So good afternoon. I will present a data set. This was one of the posters yesterday, and we already got a lot of questions about it. So a bit of context. This company here is the utility company in the state of Paraná. They provide electrical energy. The state of Paraná is about the same size as Germany. So it's a large area to cover. And they fund research. Specifically, this research was part of a call for proposals. So at the university, at UTFPR, in this laboratory, we made the proposal to work with NILM, and they accepted this proposal. They accepted this as part of research and development. In Portuguese, PD means research and development of this government agency. Well, we started our project 2 years ago, and we had a look on all available data sets that had high-frequency sampling. And we got this set here. They are all well known to you. But we were not satisfied with the characteristics of them. So we decided to have another set of requirements for our own data set. And so the basic question is, why do we need another data set? Because none of those that were there fit our requirements. Our requirements say that we need a sampling rate larger than 15 kilohertz, which is okay for those that I showed. We need waveforms for single and multiple loads. If we want to do disaggregation, we need waveforms with several loads so that we can actually try to do disaggregation. We need precise time stamping, which means that when I record a waveform of current and voltage, I want to know exactly when a given load was turned on or off. Exactly for us means, in most of the cases, I would like to know in which sample of current the load was turned on or off. In some cases, we accept that the resolution of time information goes to one cycle of the mains. And we also want multiple scenarios. We started with residential, but we are planning for commercial, industrial, and also we want fault scenarios. So we're starting by building a jig. In this jig, we have 8 outlets where we connect 8 loads. We have so far a total of 27 different loads, and we connect 8 of them. And we control the order and the timing where each load is connected. So there is a command module here. It will activate concurrently a relay and a triac. The triac is important so that I know exactly in what angle of the mains I'm turning the power on or off. Otherwise, the relay has a few milliseconds of delay before it connects. And the relay will guarantee that even when I change from one cycle to the next one, there will be no interruption in the power. At the same time that the command module commands the relay and the triac, it also sends information to the recording device down here. So the recording device is monitoring sensors. They go through a signal conditioning block, and then it records with a resolution of 12 bits. So our ADCs are 12 bits. We connected a scope with a current probe so that we can validate all the measurements that we'll do with this sensing here. This is an actual picture of our jig. At the beginning, these wires were well put into a plastic, but we moved it so much that it ended like this. You see here the relays, the triacs, the 8 outlets. This is the signal conditioning module and the microcontroller from National Instruments that does the recording. Here you see the current probe and the protection of the jig. This is the sort of information we collect from the jig. So a situation where we have a single load, turn it on, a spike in the rush current, and then the load stays on until this time when it's turned off. And another situation where I have two loads. So first load is turned on, second load is turned on, then the second load is turned off, and finally the first load is turned off. This was our first approach. We started it last year. We already collected more than 1,700 waveforms, and they are all available on our website. But we thought, well, what I'm doing is I am controlling the load shaping artificially. That's why we call it the synthetic load shaping sub-dataset. It's not exactly the real world. So we would like to collect data from the real world in a house or even in our lab. But then we come to the problem, how are we going to know the precise moment that a user turned a given device on or off? And to solve this problem, we devised a network of low-cost devices. Low cost means that every device costs less than $20. And even so, they are very precise. They have 1 millisecond of accuracy between them. So if one module collects a time information, I'm sure that it is not going to be larger than 1 millisecond the error to the next one. And this is the setting we are planning to use to collect our natural loads shaping measures. You see here the power entrance, metering, and then you have the fuse box, either from the lab or from a house. Just before the fuse box, we put the sensors for voltage and current, and then we have our trace recording and our time-based master. Everything together here. Then for every load in the house or in the lab, we have a current detector. And when there is a change in current for that specific device, we record it with an accuracy of 1 millisecond. And this accuracy is guaranteed by a network with an RF transmission from the time-based master to each one of these devices. So we keep the recording for a couple of days, maybe for a week, and after a week we collect all this information and put everything in a single file. These recordings are not available yet. We are currently building 30 of these devices. And once they are ready, we already built a few just to verify that it works. It works. So now we are building a lot of them, and once they are ready, we'll start collecting data. So soon we will have this available on our website as well. This is another presentation of the same picture. So you have here the time master, all the devices with an RF connection among them so that they keep time. And you have here specifically the components that we are using for each one of these devices. And you have a picture of these components here. So it's a very low-cost microcontroller, a current detector. We are not measuring current here. We are just detecting if the load is on or off. Okay? And then we have a pair of RF transmitter and receiver. Then we come to our third approach. So I would like to collect data in situations that are hard to do in the real world. For instance, if I have a motor and one of the windings get a short circuit. It's a situation that I would like to detect, but it's not easy to do it. So we decided to have a third subset, which are of simulated loads. So the loads are simulated in an environment using MATLAB and Simulink. And we can play a lot with the number of harmonics we have in the main signal, the inductance of the lines, the noise that we aggregate to the system, and obviously the faults. So this is the simulated environment, very similar to the other ones. So far, we are working with up to 5 simultaneous loads. We chose 5 for a practical reason. It takes a lot of time to do every simulation, so as you increase the number of loads, it takes longer. These are the 7 simulated loads we have so far. So from a very simple resistive load to a more complex universal motor. And for each load individually or in groups, we have subsets from an ideal situation to situations where you have inductance in the power lines or where you have white noise being added to the mains voltage. Then we compared our simulated devices to real devices. And this is the sort of result we get. So the simulation is the full line, and the real device is the dotted line. And you can see here that they look very much alike. We worked a lot on the models so that they would effectually simulate the real device. Some more experiments with more than one load. And I would conclude the talk with the figure that we had yesterday on our poster. So our data set is composed of 3 subsets: the synthetic load shaping, the natural load shaping, and the simulated loads. This one collected with the jig, this one collected from a real environment and just monitoring each individual load when it's on or off, and the third one is the simulated. For all 3 of them, we have exactly the same file format, so that once you read one or read another, it's the same program or scripts that you need. We provide in our site the MATLAB scripts needed for you to understand the files. The files, they are coded in binary so that they are the most compact as possible, but the scripts are going to understand this coding, and we'll present them in a way that's adequate for MATLAB. In all of our subsets, we have event labeling and we have event detection. So we show exactly the moment where the loads go on or off, and we tell you which load is going on or off. You can access our data set using this QR code or just taking a note of this link. And recently I asked the people that take care of the NILM wiki to add our data set to the table of data sets they have on site. I suppose in the near future it will be there. These are the references, so published papers from our group. Actually, just the first one is already published in last year. It's available in IEEE Explorer. The other 2 were accepted, but they are not published yet, so they will be available soon. And that's it. Thank you very much.